Cultivating the Sociome, Governance Without Governors, by Eric Moon. Chapter 3, Lessons from Fractal Geometry and Nonlinear Dynamics. The purpose of the discussion in this chapter is to introduce some elementary features of this fascinating topic, to note the sheer fun of learning about it, and eventually to focus on one particular feature which arises from the study of fractals and nonlinear dynamics, which is foundational to the notion of societal governance without governors. Allow me to lead you to the conclusion that I find so interesting and which I believe to be so applicable to the study of political economy and much else. Imagine it if you have not seen it, and remember it if you have. Or go have a look. A river current flowing into advancing ocean surf. The river's current has kinetic energy, and so do the ocean's waves. What happens when these energies tangle? Find a video, watch it more than once, and pay close attention to details. Notice that the energetic tangling of the river's current and the ocean's wave triggers an astonishing amount of complexity, both in the ocean's waves and in the river's current. And things happen that might seem counterintuitive until you see them with your own eyes. For instance, the ocean's waves continue to propagate up the river against the river's current for quite some distance, unless the current is overwhelmingly powerful. And the river's current flows into and through the advancing waves. The flowing current and the advancing waves, both singly and together, sculpt the ocean floor and the riverbed, including the ground on the sides and the bottom of the river's channel, in complex patterns. And the sculpted ground in turn influences the flow of the water in a dazzlingly complex interplay. This phenomenon is a lovely example of a dynamical process with fractal characteristics that occurs in nature, one of a vast number of such dynamical processes that occur all around us continually. For much of Earth's recorded history, there have been hints, especially in the world of art, of a level of understanding of what we now call fractals. See, for example, the waves and the clouds in the famous paintings of Katsushika Hokusai, a Japanese artist who lived a couple of centuries ago and whose work was introduced to Europeans during his lifetime. Consider the Asian concepts of yin and yang, which also demonstrate a kind of fractal structure. I am told that any manifestation of yang can be further divided into its own yin and yang, and vice versa, and so on ad infinitum. This is an instance of the fractal principle of self-similarity across different scales. The spark that in modern times ignited the thinking about nonlinear dynamics was struck in the field of weather forecasting. A meteorologist at the Massachusetts Institute of Technology by the name of Edward Norton Lorenz more or less stumbled upon the idea of deterministic chaos and recognized it as significant. In a famous story, Lorenz, who was working on computer-assisted numerical weather forecasting, was running some computer simulations of weather outcomes involving a particular set of variables. At one point, he wanted to repeat a simulation that he had already run, but this time he started it in the middle instead of at the beginning to save time, using as input for the new run the data as it had been printed out at that point in the original run. To his puzzled amazement, he then observed a significant departure in the results produced by the second run compared to the results of the first run. The explanation for the phenomenon he observed turned out to be that the data taken from halfway through the first run that had served as the inputs to start the second run had been rounded. The minute variations between the actual numbers from the first run and the rounded numbers was enough to send the simulation on a qualitatively different path. This was an instance of sensitive dependence on initial conditions, also known as the butterfly effect. And it is a commonly encountered feature in systems where the dynamics are nonlinear. Nonlinear just means that the magnitude of a response can be out of proportion to the magnitude of the input. Shortly after Lorenz's heyday, the brilliant and intuitive French mathematician Benoit Mandelbrot published The Fractal Geometry of Nature. This treatise, with its rigorous quantitative exposition, made a huge impact and opened previously unimagined vistas in science and philosophy. Mandelbrot knew of Lorenz in his work with deterministic chaos and complex natural patterns. And although he came at the investigation from a different angle, he and Lorenz ended up in pretty much the same place. Both scientists were talking about strange attractors. And Lorenz himself created the Lorenz attractor, which fits the definition of strange, and another one worth looking up on YouTube. Mandelbrot's geometry of fractals is linked with the dynamics of chaos, as introduced by Lorenz. Both men realized that new mathematical methods of investigating nature were called for. The scope of mathematical descriptions of the natural world had until then been limited to things can be thought of as smooth, differentiable in math speak. Think of a sine wave, for example, which has a definable tangent at every point along the curve. Mandelbrot showed us that we can also employ mathematical methods to describe things that are rough, that is, things with corners, which do not have definable tangents at every point along the curve. Have a look at the Weierstrass function, which is continuous, unbroken, and which has no unique tangent at any point. We can also gain insight into turbulent flows. Think, for example, of the steam rising from your morning cup of coffee. For a certain distance, this steam might rise along a predictable path in what is referred to as a laminar flow, but it leaves the smooth path and quickly becomes turbulent as it continues to rise. The resulting pattern is so complex and varied that it becomes impossible to predict. If you can imagine yourself massless and very small and riding on a particular water molecule within the steam, there is no way you would be able to predict with any confidence where the molecule you are riding on will be in the near future if the flow is turbulent, because you would not be able to measure the current state of the molecule with sufficient precision. Traditional methods of mathematics can deal well with laminar flows, but not so well with turbulent flows. And although the methods of fractal geometry do not lead us to precise predictions of future developments, they can reveal useful insights into how complex systems evolve and how the attractors and strange attractors function within these systems. I'm calling attention to fractal geometry and nonlinear dynamics because they reveal something quite valuable as we pursue our aim of creating a meaningful worldview, namely that many natural phenomena are not merely difficult to predict, but are fundamentally unpredictable, and that any valid worldview must take into account this unpredictability. To understand nature's unpredictability, it's enormously helpful to understand fractals and nonlinear dynamics on some level, and especially to understand the nature of the strange attractor. If you are among the few who can deal with the formal mathematics Mandelbrot gave us, good for you. But even without much training in mathematics, you can still gain useful insights into fractals. If you wish to go deeper, you might want to begin by reading Mandelbrot's memoir called The Fractalist, which he worked on all of his life, and which was published shortly after he died in 2010. His memoir reveals fascinating details about his intellectual journey from childhood on, his formal education, his work as a mathematician, and about his rare intellectual gifts, particularly his unusual ability to create visualizations of mathematical concepts as a key to deep understanding. So let's step onto the road of understanding the phenomenon of the strange attractor and why it is significant. Here are a few basic concepts in fractal geometry. One key concept already alluded to above is self-similarity across scales. An example that helps to illustrate this idea is the structure of a fern, which is a leaf that is made up of smaller copies of itself. For a truly dramatic illustration of cell similarity across scales, search YouTube for Mandelbrot set zoom. And notice the similarity of the patterns being generated as you zoom in or out. The Mandelbrot set is probably his most widely known contribution, and it is generated by a large number of iterations of a relatively simple equation, at least if you consider a discussion involving complex numbers to be simple, where the outputs of one iteration are used as inputs for the next iteration. The images look the same somehow, that is, they have the same general shapes no matter how far you zoom in or out, and old patterns, such as the original beetle called a baby Mandelbrot, reoccur in a way that is almost but not quite identical to the original. Another useful concept as we build an understanding of fractals is fractal dimension. You might have encountered a fractal image somewhere or other and noticed that its fractal dimension might be given as, for example, 1.7 or 2.4. What does such a thing mean? We all know there are 3 spatial dimensions in the world we live and move in, and apparently one temporal one. Common sense tells us that any object exists in some integer number of dimensions. Are mathematicians just wacko? I hope you will be happy to hear that there is a fairly accessible meaning of fractal dimension which does not contradict the intuition we have of spatial dimensions, and which will help you to understand the rest of the discussion about fractal dimension. In traditional geometry, for example, you have a line with 1 dimension, a square with 2 dimensions, and a cube with 3 dimensions. But many natural objects and mathematical sets do not fit neatly into any of these categories. Think of a coastline, which is more than a line and less than a surface. Think of clouds, which are more than a surface and less than a volume. For an intuitive grasp of fractal dimension, think of how the amount of detail changes as you zoom in. Fractal dimension measures how efficiently the object fills the space on each iteration, where efficiency is defined as how aggressively the expanding object occupies the available space when you observe it at finer and finer scales, or how much does the amount of detail change as you zoom in. For an intuitive insight, think of a coastline which has a fractal dimension greater than 1 because more detail keeps appearing as you zoom in. People have calculated the fractal dimensions of actual coastlines and have determined that the fractal dimension of Britain's Island, for example, is about 1.25, and the fractal dimension of Norway's coastline is above 1.5 because of its fjords. If you find this stuff interesting, I encourage you also to have a look at the Sierpinski triangle, which exists in a 2-dimensional space and has a fractal dimension of 1.585. The object is created by a repetition of a process that begins with a filled equilateral triangle where you create and then remove a smaller triangle from the filled portion, which you have formed by connecting the midpoints of each side of the triangle. As the number of iterations approaches infinity, the area approaches 0, but the perimeter increases without bound. Without bound means there is no finite upper limit. Then look at the Sierpinski pyramid, which exists in a 3-dimensional space, but which has a fractal dimension of 2.0. How weird is that? The pyramid is formed in a way similar to the formation of the triangle, except you are successively removing tetrahedra from a 3-dimensional space instead of triangles from a 2-dimensional space. The volume approaches 0 as the number of iterations approaches infinity, and the area increases without bound. Now we get to the really good stuff. Let's elaborate on the term strange attractor mentioned above. This is the concept that has arisen from the study of fractal geometry and from the study of nonlinear dynamics that most helps us to get it, why natural phenomena can be so unpredictable. A simple attractor is any set of points around which the results of a dynamical process may gather. Examples would include planetary motion and pendulum motion. An example of a dynamical process that results in a strange attractor would be the relative proportions of the populations of predators and prey. Think, for example, of coyotes and rabbits. If there are a lot of rabbits, coyotes will kill and eat a lot of them, leading to an increase in the number of coyotes. But since there now aren't as many rabbits left, they will become more difficult for the coyotes to find, and this puts the brakes on the number of coyotes who can survive and reproduce. Fewer coyotes then results in more rabbits, and so on, in a repetitive dynamical process, in which neither population is likely to either explode or go extinct. Proportions of rabbits and coyotes will settle in around a set of figures, and this set of figures is a strange attractor. It's a strange attractor because trajectories of populations never repeat exactly, even though they are confined to a particular region in phase space, and the system exhibits fractal characteristics. If you plot the trajectories on a graph, it will typically resemble the butterfly shape, similar to the shape revealed in the Lorentz attractor. This strange attractor embodies the balance in each population between growth and decline. The populations rise and fall unpredictably, even though it's a deterministic system. And now we are getting close to the heart of the matter, and we can explain why so many of the phenomena in the natural world, including the world of human society, which is as natural as anything else, are unpredictable even when deterministic. A dynamical process centering upon a strange attractor has the feature of sensitive dependence on initial conditions, sometimes referred to as the butterfly effect. Very small changes in initial conditions can lead to very large changes in future conditions, and vice versa, and to qualitatively different developmental paths. What are the implications of the butterfly effect on the effectiveness of weather forecasting or economic forecasting? Let us say, for example, that you would like to make a forecast of some future state of the economy based on measurements of the values of the variables in the current state of the economy, such as output, employment, investment, inflation, etc. Your reason for making the forecast would be to enable an effective intervention in economic activity in such a way that good outcomes will result. If you have been paying attention in the real world, you know, of course, that economic forecasting is notoriously unreliable. The jokes abound. One famous quip was that the only thing economic forecasters have so far accomplished was to make weather forecasting or fortune telling look respectable. Another quip was that economic forecasters have been able to predict 9 out of the last 5 recessions. The principle of sensitive dependence on initial conditions, the butterfly effect, gives us insight into why it has been, is now, and always will be true that economic forecasting is intractable, and would still be intractable even if we were to get better and better at modeling the relationships among the variables. The problem that must be solved if we want a reliable forecast, and which cannot be solved in practice, is that the current value of each economic variable must be measured with infinite precision, which would take an infinite amount of time, in order for a forecast to produce results you can trust. It ought to be obvious that we will never be able to do anything like that in practice, and merely getting the measurements close doesn't help. Creating a reliable forecast would be a necessary first step in the attempt to control economic outcomes. If it's not possible to produce a reliable forecast, it ought to be abundantly clear that we cannot hope ever to control outcomes. And even if we did have the ability to produce a reliable forecast, further problems and failures would arise when we attempted to carry out the intervention, and for the same reason that forecasts fail, namely the butterfly effect. We need to stop going back to the drawing board. We must find an entirely new approach to governance if we seriously desire a better world for ourselves and our progeny. How about governance without governors? Coming next, Chapter 4, Value and Price, Two concepts that we need to understand if we want to understand how it is that governance without governance can actually take place.